sorry for the technical issue. So let's start. Dan couldn't make for today's class. He's traveling, so I'm replacing him. We have lots of stuff to talk about, so get excited. Before starting the main topics, we have some stuff about administration. Homework 0 grades, I've been told that they're up. Homework 3, the due is tonight. So try as much as you can. I think one of the TAs has office hours today, so try to go try to like push him so that he gives you the answers. And homework 4 will be released next Tuesday. So try to start working on it as soon as you can. Don't just like start like the last days. Almost every day there's a TA that has office hours. So go to their office, ask them questions and stuff. So try to be active. And also deadline for proposals. We have projects for the class. I highly recommend that you form a group and try to work with others. Just doing the project with other people in group has lots of benefits. So I definitely recommend that. And that's also gonna make the life of TAs easier. So also, okay, so how many people want to do in group and they already have a group? Raise your hands. Okay, that's a good number. And how many people just want to do it alone? A few. So I assume that the rest, they want to do it in group and you don't have teammates, right? Raise your hands. I think we are missing some people here. That's okay. So if you don't have teammates, try to find someone. Okay. Any questions from last time? No questions. Moving on. Okay. Just a quick recap of what we talked about last time. We started the discussion on neural networks. We said, okay, so we introduced a special family of neural networks. They're like one of the oldest members in this family, a multi-layer feed-forward neural networks. And we introduced a bunch of algorithms for training this, most importantly, backpropagation algorithm. So a question. Someone, please, in a few sentences, say something about neural networks and backpropagation. Anything. Anything that you remember. What is it? What did we do? High-level idea.
The chain rule of couplets.
Okay. Chain rule. Could you elaborate more?
Backpropagation is essentially chain rule.
Exactly. Backpropagation is exactly chain rule. Okay, that's a very good point. What's your name? Hongwei, you deserve extra credit. So someone else, say something different.
So basically, all the network is just like a composition of perceptrons. Backpropagation rule is just like we're just taking lots of local partial derivatives and going opening the derivatives, we're finding the way how to update the weights.
So he mentioned 2 points. It's a composition of a bunch of neurons. So like we have these basic units, and we compose them. They are connected to each other. Like they compute and give the value to the next layer, and we continue this on and on. Another point that he mentioned is in order to train this, after calculating the values at each of these units, we propagate back the error values to the previous steps. And that's how we use those gradients in order to update the weights of the previous layers. What's your name?
Michael.
Michael, thank you. I just want to thank you. So, okay, yeah, so at this point, I can say that you know most of the things about neural networks. So just understanding how backpropagation works is the biggest thing that you have to learn about neural networks. The rest is different variations of this algorithm for different structures, right? So today we are gonna see 2 other families, two different architectures of neural networks, and they're gonna look slightly different or very different, but the underlying idea is the same. We're gonna compute the gradients in the last layer, previous layer, and so on, right? So the idea is the same, right? So let's start. So something Okay, so before jumping into these two new architectures, let's start with this idea which we didn't address last time, but it's relevant to almost all of these architectures, and in a sense, it's relevant to the whole machine learning problem. And it's the idea of someone gives you an input, and we want to solve it. How we are gonna encode those values into our mathematical model, right? And how do we humans, how do we do this in nature? So we humans, we have like, we have some sensory elements in our body, like ears, eyes, and that's how we get the information from nature, right? And neural networks need eyes, they need ears, right? That we have to encode information. The information can be picture, it can be sentence, can be audio. We have to encode these information in neural network language, right? So that's a big challenge. I'm not going to give a concrete answer to this. I'm just trying to say that this is a big challenge. People have come up with different ideas for doing this, for different tasks, for different types of data, but we still don't have a good ideal solution for this. So we are just going to go through a bunch of ideas, right? So this is just a bunch of ideas. And in neural network jargon, it's called receptive fields. Like all these, and this is coming from biology, like all of these neurons, they have this input layers, input connections that connects them to the previous neurons. They call it receptive fields, like they receive stuff from their input. So consider this problem. Let's make it more concrete. Let's fix the problem and think about that problem. Let's say we have, the task is doing some sort of prediction on an image. Right? So I give you an image, and I say, okay, so you can use neural network, and you have to predict something. For example, the prediction task is whether there is a face in this picture or not. Right? How would you do that? How would you go about converting this image and feeding it into neural network? Say something random, just throw ideas at me. Good idea. See if we can detect edges. Okay, so let's make it more concrete. So I give you an image. You don't know its size. And what would you do? Connect it to what you said. You said connect.
Look for sharp contrast in colors.
Okay, so I suppose let's make it simpler. So let's say you have this filter which tells you how edgy is this picture, right? So somehow we find it, we create it. I don't know how you want to build it, and that's the input value that we give to the neural network. So based on his encoding, the whole picture, no matter how big it is, it can be big, it can be small. It's going to be converted into one real valued signal. Right, so is this ideal for detecting faces? More ideas, but that's a very good starting approach.
An input would be basically a combination of all the pixels. So one pixel would be one input node.
Say it again.
Each pixel will be an input node for the neural network, basically. So we map every single input field as a pixel.
Okay, so the idea is for each pixel is going to be mapped directly into a neural network. What is the problem with this idea? Too many pixels? That can be a problem, but bigger problem. Let's say in the training data set, I give you only faces of size 50 times 50, right? But maybe in the test time, I want to give you bigger pictures. You cannot just change your architecture. You have trained your neural network, it's fixed. When you test it, you cannot change the architecture, right? So if you give like each single pixel to one unit in your neural network and the architecture of your neural network is matching that size, it's gonna be it's gonna work only for that size of pictures.
We can rescale different pictures to that size always. For example,
okay.
50 by 50 all the time and then rescale any
Okay.
arbitrary.
Yeah, that's also a good idea. We can scale it, but again, it's probably not ideal. So, okay, let's move on. This is his idea. Sorry, what's your name?
Andre?
Andre. This is Andrei's idea. Andrei says, okay, so I get a picture. I'm going to give all of these values. I'm going to give it to like each of these input units, right? So so one issue is, this is like actually different. So, okay, so no, actually this is different from his. So this idea is saying that for each of these units in the input, give all of the pixels to that unit, right? So the problem with this idea is that this is going to work when you have different size pictures. But the problem is that this network doesn't have any understanding of these local connections and like local information between the pixels, like whether this pixel is on top of this, below this, like that, like local correlations.
I suggest another idea.
Yeah.
Can we just like perform picture could be performed as three separate three-dimensional functions, right? Like RGB. So can we just like somehow approximate those functions in three-dimensional space and give them as input to the neural network?
Approximate them?
Yeah.
I was lost at that point. Approximate what exactly?
So basically, if we have a picture, so we can say that our like x and y dimensions are just like the dimensions of a picture, and the third dimension will be the value of the pixel. For example, for red color. So for each of the color slices, we'll make some discrete function, and then try like with some regression, try to approximate those functions and give it as an input to the neural network.
Okay, I didn't completely understand, but I think, Michael, you're too smart. I don't get your point. Let's talk about it after class. Okay, so back to this. The problem was that we lose this spatial correlations. What we can do is, okay, how about this? We are gonna like, rather than getting all of the pixel information on all of the information on this whole image, we are gonna create like small blocks. We are gonna say, okay, each unit is responsible for this like certain block of the picture, right? And as you can see, like here, my blocks are disjoint. So inside each block, we have the same problem. Inside each block, I lose the information, the spatial correlation information. Right? Another issue is, although like between blocks, my network can learn the spatial correlations, but the issue is that like these disjoint blocks, when you disjoint them, there's like gap between like the pixels of this block and this block. Usually, one property in all of the images is that like the values of pixels, they change smoothly as you move on pixels, right? So when you have these disjoint blocks, you will lose this like the smoothness property between blocks, right? Again, this is not ideal. So something that people do commonly these days is that they try to have these blocks. Okay, so it's not really a block. So okay, so people usually try to approach by creating a filter bank. So what is a filter bank? Filter bank for images is just a bunch of matrices. Each of these filters, they scan the image one by one. Like they start from like that corner, they scan this and move to this corner, continue doing this on and on and on, and they create different outputs. For each filter, you have different output. For example, one example of filter can be a filter which is sensitive to sharp corners, the idea that someone mentioned here. And using this, you have not only you preserve the correlation, the spatial information between filters, right? So you also get the property that someone was pointing at. I can create different filters which are sensitive to different properties, right? And we are gonna see that this idea can generalize to our other problems too. For example, text. I'm gonna show you an architecture which works on text. So okay, so before moving on to that text part, let's try to like open this idea and try to like look inside that more carefully. So this is gonna start the conversation of convolutional neural networks, which they're like huge in computer vision now. Okay, so first, so they're called convolutional neural networks, but nowadays people don't actually do. So convolution is a mathematical operator. If you are electrical engineering majors, you definitely know what the definition is. But nowadays people do something like convolution. It's in practice people do like element-wise matrix multiplication. But I'm going to give you exact definition of convolution because I think, we are studying convolutional neural networks, we have to know what is convolution. So this is the exact definition of convolution in one dimension. Don't be scared, the definition looks scary, but the actual operation is simple. So this is on continuous space. This says convolution of x function, so x is a function of t, h is a function of t, let's say x is input, h is a filter, and they're both on defined over t space, and we want to find their convolution, and convolution is just one integration of x tau, the variable that we're integrating on is tau, x of tau, h of t minus tau, right? So this is the definition, and you can discretize this, and you will get a discrete version of this convolution. Let's just try to open up this definition because it's not really clear what's going on here. So let's say this is xt, this is our input, and this is the function, this is the step function, and this is h of t, right? So it starts from this value and goes down like this. And what we are going to calculate is this convolution. This star always shows the convolution. We are going to calculate this. So what's going on here inside this integration is that this h of t minus tau, note that the variable that we're integrating on is tau. It's like reversing h of t on its x-axis, right? So I'm gonna reverse h of t, and it's gonna look like this, and I'm gonna keep x of t here. So what's gonna happen is that I'm gonna change this value of t here. Here you can see that t1 is here, and I'm gonna for each fixed value of t, I'm going to find the area under the curve of their multiplication. So when you multiply this by this, the area under the curve is 0. And when you change the value of this parameter, instead of t1 you have t2, it's moved here. The area when you multiply them, this is the intersection. So this is the area under the curve. It's growing bigger, right? So this is the result of convolving this function with this. This is the result. So if you don't get this, don't be scared. Everything is fine. You can still follow the conversation. Everything is fine. But I just wanted to show you the actual exact definition of a convolution. And you can always come back and see this definition. But it's not really that important for the rest of our conversation. Okay, so let's see how convolution works on images. Right? So what this is, again, this is the problem. I have an input. The input is an image. And I have another something like image. It's like filter. It's another matrix. Let's say this is my matrix. This is okay. And I want to convolve this with this, right? So what I would do is I would inverse this into dimensions, right? So like flip it, and you multiply this matrix. Start from this corner. Multiply by the values of the image, right? For example, here, this is 0, this is the same, right? -1, 0, right? And multiply this by the values of, let's say here, the values of each pixel, and sum them up. This is the sum, and put them in the new picture, right? I keep repeating this for all blocks of size 3 in this image, right? The resulting is going to be another picture. Did you get this part? How we jumped into this picture from this to this? Yes, I see some yeses. I'm looking for no's.
How did you choose the boundary?
Oh, that's a good point. People usually, okay, so it's really your decision. Either you can start from like inside the boundary, or something that people sometimes do is they zero pad. They add extra fake 0 values, like they add extra margin, and you go beyond the actual picture. Good question. Yes?
Actually, could you please once again explain how this filter thing solves the problem with a fixed amount of perceptrons in first layer of network.
We haven't gotten to that point yet.
Ah.
Wait for it. Yes. Wait for it. Yes.
How do you get that small matrix, that 3 by 3 matrix?
This one?
Yeah.
For now, let's fix it. We will train it. We will train that. Okay. So, but another point here. Okay. So something that I was trying to show is that this is how I apply a filter on an image. But another point to notice is that this filter sharpens our picture, right? So this is, you can come up with other filters to, for example, make it less sharp, make it noisier, make it like, for example, a filter which is sensitive to like different edges, like with angles and stuff like that, right? And we are going to learn those filters.
What about the summation is greater than 255?
You can truncate it. It's not very important. You can truncate it. It's like a bunch of. This is something that, depending on your problem, your architecture, you have to decide. I mean, for now, it's not a problem for us. You can truncate into 255. Okay. So again, doing the convolution. Let's say we have a filter of size 3 times 3, and this is our input. I'm gonna multiply on this. I'm gonna multiply it element-wise with these matrices, with these values, and put the value here. I'm gonna slide this, keep repeating this, and put the values here. I'm gonna continue this until I'm done with all of the values here, right? This is the output, right? In practice, how do we do this? This looks like this is a very computational intensive operation. In practice, we don't actually multiply the matrices. What we do is we do something called fast Fourier transform, right? Or people call it FFT. And FFT is almost everywhere. Like whatever devices that you have, they have like very fast components for doing FFT, and it has super fast. Like FFT is one of the classic algorithms in electrical engineering. That was just for FII. It's not very important. Yeah.
And how FFT solves the problem here?
Good question. Beyond the topic of this class, FFT stands for fast Fourier transform.
Yeah, so basically we're just finding amplitudes for like particular frequencies, right?
It turns out that convolution in time space is equivalent to multiplication in Fourier space. They use these properties to make the calculation of convolution faster. Right, so, but let's not get into that. Okay, so far this is what we have. We have an input, and we have this convolution layer. And for a given filter, we're going to get one output. If we have multiple filters, let's say I have 4 filters. For each of these filters, I'm going to get another output, right? So I have 4 filters for a given input. I'm going to get 4 outputs. And if I have, let's say, if my input, he was talking about having multiple channels in the input. Let's say if I have if a channel for blue color, one for red color, one for green color, I'm going to have, for each of these, I'm going to apply them on the filters. I'm going to have extra outputs, right? So this is what we have so far. So okay, back to one of the questions that we were thinking about at the beginning of the class. We have now all of these, their size is dependent on the size of the inputs. How are we going to handle this? So people in community currently use an approach which is very simple. You're going to be shocked how simple this approach is, but it works. That's the point. It works, right? So what we do have here is that like we apply our filter, we get an output in the output of convolution. We want to make it fixed size, define fixed. That's your decision. So one way of doing this is let's say you want to convert this block to a fixed block, to a fixed size block that you decide is size, right? You're gonna choose the maximum value from this bigger blocks. It's called max pooling, or you can average them. This is very simple, right? Or do any sort of combination of these values so that the values get combined and give you the smaller size blocks. So this is called pooling step. Like you get a bunch of values, a pool of values, you combine them somehow, and you get fixed size values, right? So combining convolution and pooling is this is usually known as one step in this stack of one stack in the stacks among other stacks of convolutional neural network. Right? Any questions so far? So this is what I have so far. I get an input, I convolve it with my filters, I get a bunch of output, their variable size, I do pooling, I bring them down, I shrink their size to my desired size. This is what I have so far. Right? So this is what this whole thing is doing. And guess what? Very simple. I'm going to stack these structures. I'm going to put one of these here. I'm going to put one of them here, put one of them here. And I'm going to keep repeating them as many times as I want. And in the output of this, I'm going to get a bunch of values that have, they have fixed size based on my design. And their number is dependent on the number of the channels in my input and the number of the filters that I have. Again, they're my design choice. Now here at this stage, the values that I have, the vector of values that I have, they're fixed. I can just give them to a fully connected layer that we learned last time. And based on that, I'm going to make a prediction. Right? So this whole thing is called a convolutional neural net. Yes?
Basically, we have like a picture. The first stage changes its dimensionality, and all other doesn't change. Do not change dimensionality, right? It's just like...
Be louder, and because other people in the back also need to hear. Yeah.
So basically the first stage, it changes the dimensionality of the image, and all others think that the previous stage is an original picture, but doesn't need to be changed. But the dimensionality of the previous picture doesn't need to be changed, right?
No. Wait, is that a question or? Okay, which part of it you're confused?
I think I will ask after.
Okay. Okay, let's talk about that after class. This is a real example of, I'm taking this picture. This picture is taken from the first paper that proposed ConvNet from a paper maybe like 20 years ago by someone called Jan LeCun. And it's commonly known as LeNet because his name was LeCun, LeNet. So this is the diagram that he has. A picture is given. He somehow converts these, creates like different feature maps from this input image. It can be applying a filter on top of this. And what's happening here, instead of, okay, he calls it subsampling instead of pooling, subsampling, convolution, subsampling, and then we have a bunch of vectors and we connect them in a fully connected network and we have output predictions. Right? So this is, people do this and it works for people. Okay, so I wanted to show how we can derive backpropagation for this, but I think it might be better not to go into too much details because really details here doesn't matter. As long as you understand how backpropagation works, you can just derive everything yourself. So, because everything is very simple. Convolution is a linear operation. You can add nonlinearity on top of that, and you doing chain rule for these linear operations is very simple. You can just do it. I'm gonna show you the equations, but we won't go into details. So what we do here is, okay, first step, we calculate, someone gives you an error function. Someone gives you, okay, someone tells you that this is my loss function, and based on that, you can calculate the error in the output. This is my error in the output. I can calculate the error, the gradient with respect to output prediction. And this is our fully connected layer from last time. We learned how we can propagate back the error to the first layer. So we are going to repeat the same equations, and we are going to get the error in this stage. And we are going to keep doing this. We are going to keep using the chain rule, and we are going to propagate the gradients up to here and here until we are at the first layer. So relatively straightforward. So the equations here, but let's just keep them. If you have time, we can go back to them. If you're interested, I can go through them, but it's just you're gonna fall asleep. Okay, so let's get more intuition about this convnet. What's going on? So this is, okay, so in the first stage, we have this convolution with a bunch of filters. We have another set of filters in the second stage, and same thing in the third stage. What do we learn? What do we train? What are our weights? Yeah, that's actually a good question. When we are training, what are we training? What are our parameters? I want to see how much I confuse you. Convolution weights, yes, the filters. They're the stuff that we are training, right? So let's say our task is whether there's a car in the picture or not. But we're training, it's our filters at each stage, right? And usually in practice, something that people observe is that in the early stages, the filters are sensitive to more general, less detailed elements of the pictures. For example, like these are the filters in the first stage. And these are, okay, so to be more accurate, these are the results of applying filters in some sample input from the results of applying filters on some sample input. But as you can see is that like these filters at this stage, they seem to be sensitive to more detailed pieces of the picture, right? And you can see it's getting more details in the final stage. And this is from real pictures, so this observation happens in reality. A little bit of history. So convnets were first introduced by this person and maybe like 25 years ago. They seem to be simple, but people kept doing it, and they work a lot well in vision tasks. It's very common now in the vision community. This is a convnet architecture from a project that some people in Google did. You can see it's like so many layers. You can't even like read what's going on here. But they're like, this is like variation of convnet. It's slightly different. So instead of like having one single convnet here, they have like multiple threads, multiple convnets with different sizes. So they do it for different reasons, which are beyond this class. But the idea is really the same. If you understand what's convnet here, you can just go and find their paper and read the details. It's really understandable. You can just read it easy. Okay, so I wanted to show a demo, but since we had some technical difficulties, let me try again. Okay, so this is a convnet which is running live on the browser. Someone in Stanford, a recent graduate from Stanford, did this. As you can see, this is you can see my mouse, right? This is the loss function under training data. I think training data. It's mostly consistently going down. Sometimes it has like these bumps up, but you can see the loss is going down, and really the whole definition of this convnet is this. It's very simple. You have the input layer, you have the convolution layer, you have pooling layer, conv layer, pooling layer, and a softmax in the output layer, which is a matrix multiplication and choosing the maximum value, right? And as you can see, this is the input value, we are applying this. We are applying convolution. We are convolving the input with these weights, with these filters. These are the results of applying the convolution. We are doing thresholding on top of the values. We are doing pooling. You can see the values the pictures are smaller here. Again, we do another convolution layer, thresholding, pooling, and here we have softmax, and after that we have prediction. And these are the prediction are a bunch of sample test data set, test images. So the green ones are good, red ones are bad. And you can see that it's already like after like a few minutes of training on my browser, just JavaScript, it's getting a relatively good performance just by looking at the predictions, right? So, another thing I wanted to mention is that this, like really creating these models are just very simple. So this is JavaScript, but you can there are a lot of Python packages for creating connests that you can just look in the internet and use them. They're very simple. Okay, moving on. Another big thing that has come up in the recent years is the effect of depth. I think Dan mentioned last time that it used to be the case that people use only small depths or shallow neural networks, but recently people are trying to come up with more deeper and deeper networks, right? So these are a bunch of works from the past, past 6 years, 2010, 11, 12, right, until very recent. We can see that, and this y-axis, these blue bars, they are the errors on this famous task. You can see that these systems, they at the time they used to be state of the art. They were really good. They were breakthroughs. But the error is going down really fast, and you can see that this is their depths. These are very shallow networks. 8 layer, 1922, 152. That's a big jump, right? So it seems like you just add layers to your network and they get better and better. And why people used to like shallow networks? Because if you remember, Dan mentioned that even shallow networks, you can prove that they can represent any function. They're global approximators. Right? So people didn't even think that it might be necessary to use deep networks. So, but someone tried to use deeper network. Maybe it was a mistake, or I don't know, maybe it was intentional, and it worked better. And we almost have zero theoretical understanding of why this is happening. There are some basic results why it might help, but they're not that strong. They're weak results. Okay, so so I'm gonna because I'm trying to decide what to do now. Okay, so I think because I want to also get into recurrent neural networks, so I'm going to skip a few slides. Here I talk about some practical details of how to train contests, but I think they're not very important at this point. I think what is more interesting is seeing another family of neural networks. We call them recurrent neural nets. Let's go to that because I think that's more interesting. If we have more time, we can come back. Okay, so recurrence. Okay, so recurrence, I think they're more similar to the first family that we saw last time. We saw feed-forward networks. We had fixed architecture, something like this. They didn't have any cycles, so that was an implicit assumption. We didn't have any cycles because we had to propagate this error back, and the assumption was you don't have cycles. But recurrence, essentially they have cycles, right? But in practice, the way we implement them, we break the cycles. We apply it in a cyclic fashion. So implicitly they have cycles, but in practice, we break it. But let's see, in practice, how they look like. So let's say this is a cyclic representation of my neural network, and these are the weights: W1, W4, W3, W1. forget about initial state. That's a little tricky. Let's say we start with this like initial state. You apply W4 and you get to this point, and again you apply W3. Like you can see that you apply this, you go to here, like this. Right? So essentially you unwrap it across time. You break the cycles and you unwrap it and you apply through the time. Right? So that's how we apply recurrent neural nets. But I think it's going to be more clear if I give you a more concrete example. So let's fix it. Let's fix the task. Let's move on from the vision task. Let's think about an NLP task. The task is someone gives you a sentence, and I want to predict the part of the speech tags for that sentence. Right? So this is the task. So what issues we want to handle in this task? What are the challenges, or what kind of properties do we want to have? We have a structure. We have correlations in the input space and output space. Right? So verbs tend to appear after some certain other words, or there is a similar correlation between their tags. And some sentences are longer than the other ones. Right? So we have to handle these issues. Let's say I'll give you this task, and you want to create a model for solving this, for tagging each sentence, each word in the sentence. How would you go about solving this task? Throw ideas at me. I'm going to wait forever. Random ideas. Hmm? Oh, okay. I guess. You just woke up? No. Okay. Okay, so here's the task. I give you a sentence. For each sentence, I'm going to tag each word with a label. So in this task that I'm fixing here, the tag is part of a speech tag, right? And part of a speech tag just shows the grammatical role of that term in the sentence. Like, is it a verb? Is it a noun? Is it an adjective? What is, like that, right? So the challenges is sentences are variable sized, and we can't just have a class for an each term. You can't just decompose. Okay, so one naive algorithm is decompose each terms, give each term to a single classifier, and ask the classifier what's the label for this term. Is it going to work? Yes, maybe to some extent it's going to work, but we are going to lose the correlation between the terms. Right? So that's the task. Okay, so this is an example of a recurrent neural network that we can apply to this problem. A recurrent neural network has a hidden state. It's like memory, and it also gets some information from the input space. So x values are the vectors that you get from input value. X can be a vectorized version of a term. Hidden state is another vector. So you get an input, you combine with your current hidden state, and you get another hidden state. Right? So you keep repeating this, and you have hidden state at each time. And when I say time here, I mean each term in the sentence, time across sentence. Right? And depending on your task, you can either make prediction on each term, you can make prediction for each sentence, and so on. Right? So that's really a design choice. Right? And something very important. Let me just clarify this. This is the same structure being applied multiple times. It is not a 3-layer stacked model. This is one fixed structure. I apply it here. I get the output. I apply it again to the same structure. I apply it again. It's like applying it multiple times to itself. It's like having a cycle here. Oops. Okay. So that's the big difference from the fully connected feed-forward networks. Yes.
When we later on try to train such a network, will the weights of all the three be the same, or will they be different?
All will be the same.
All three will be the same?
Yes. But their states are different. Their inputs are different. So it can be a limitation. It can be a power, like positive point. But that's very important. Thanks for bringing that up. Okay, so I think I mentioned everything here. So you can just play with this structure and create like the other structures rather than just having like one directional structure which only depends on the previous context. You can have bidirectional structure, like all of these orange hidden layers. They depend on the previous, on the context on the left side, and they predict the context on the right side. And you can have another like counterpart recurrent net which has context received from the right side and gives to the right. And you can this is called bidirectional recurrent neural net. This is a very simple extension. You can stack them on top of each other. Like you can have, rather than having just one layer of hidden states, you can like stack on top of each other and so on. Right? Very simple extensions. So we have like, I think 10 minutes. Let me briefly mention how we do gradient descent backprog for this. Again, idea is very simple. Someone has fixed you a task. Someone tells you that this is the task and this is how you measure the error. So what I have is, actually before moving on to deriving this, what are the parameters? What do I want to learn in this model? We have to first clarify that first. What are the parameters here?
The weights for the different layers.
Weights.
You want to multiply it with your input and your input layer.
Could you be more specific?
So you're converting your first layer to your first layer, and those whatever is converting that. So for example, in the previous case it was filter, again whatever the weight is.
Okay. That's very good. Let me try to just rephrase that in a more accurate words. So here I've decided to represent all of my words. I fixed the task. I said I'm doing prediction over sentences. So I'm gonna for each word I'm gonna initialize. I'm gonna represent each word with a vector of fixed size. Right. So and I can initialize them with random weights. Right. So that representation for each word is a set of parameters that I have to train. That's one set of parameters. Right. And given this input representation, I multiply this by a matrix, and I get the hidden state from the previous stage. I multiply by another matrix and get the hidden state for the next stage. Right. So this is how I transfer from this state to another hidden state. And these matrices that I multiply, they're another set of parameters that I have to train on. And given these hidden states, this is how I make predictions. I multiply the hidden state by a matrix. I do softmax. I get an output, a distribution over the output labels. And this matrix is another parameter that I have to train on. Right? So we have so many things to train on. These are the parameters. So again, the matrix which is multiplied in order to generate the output, the matrix that gives us the hidden state given the previous state, and the matrix that we get in order to convert the input to the hidden state, and the representation of the input values. They are the parameters that we want to train on. Right? So again, what is the starting point? We get this error function. After doing the prediction in the output step, we calculate the error. And what we are going to do is we are going to propagate the gradients of this error in the output back to the parameters. So let's say we calculate the error here. We are going to propagate it back here to the matrices that we multiplied at this stage. We're going to propagate it back to the representation of the input step. We are going to do the same thing for this, same for this, the same for this, and so on. Right? This is just, yeah. Could you say it louder?
In the second step, ht is equal to f of something. That w is it wt into ht.
Are you talking about?
WH and then second term?
Are you talking about this?
Yeah.
Okay, so could you say what?
W and the subscript T, right?
This is no. This is the same structure. I don't know why I have WI here. Just forget about I. I think I here means just input, right? So it always gets multiple. Yeah, it's the same for because this is really the same. This is the same structure, same structure, same structure. And when I say structures, structure is defined by its parameters, right? Same parameters, same parameters, same parameters. You just keep reusing the same parameters again and again. Right? So let's say this is okay. So let's say this is our error function across time over all of our sentence. We can distribute the gradient across time. We are going to calculate the gradient with respect to some parameter matrix. And it turns out that what matters is, what's tricky here, slightly tricky, is finding the gradient of hidden state given with respect to another hidden state in k steps earlier. Right? So that's the only thing that you have to figure out how to calculate in derivation of the gradients. And that is actually very simple. It turns out that you can just calculate that as a result of multiplication of a bunch of matrices along the way to the k-previous step. I mean, you can think about it and see that it makes sense. I think it's better not to confuse yourself. Don't be scared that it's not that complicated. It's essentially applying the chain rule and using that definition here. It's the same thing, right? So really, backpropagation on this network is simple. But something to observe here, and I think it's a very important issue to notice, is this. So we found somehow, we figured out that the gradients that we calculate, they are dependent on the value of this multiplication. If the norm of the values in this multiplication are smaller than some certain values, some certain bound, you're going to see that this is going to be smaller than those bounds to the power of k, depending on, and k is how much further back we are updating, right? If these values are smaller than 1, if this bound is smaller than 1, and you are updating your gradients 10 steps earlier, this gradient is going to be super small. This phenomenon is called vanishing gradients. The gradients in the earlier stages get very, very close to 0. They just disappear, and training those parameters in earlier stages become very hard because the gradients are just very small. And this is a serious issue. This is a serious issue that a lot of researchers think about. It's like a serious research problem. And this is not specific to just recurrent nets. You will have similar issues in multi-layer feed-forward nets, the one that we learned last time. As if you have a really deep network and you want to apply gradient descent, the gradients in the earlier stages can be very, very small, vanishing gradients. Again, the question is how you want to train a network which has more than 10. So I showed you pictures of like results from works that have like more than 100 layers. So they manage to do some stuff that they manage to train such networks which that much hidden layer. So it's not just like applying the same ideas to that networks. They have come up with smart, interesting tricks that lets them train such deep networks. So it can be very tricky. This picture, this is just like a very simple experiment. So here we have a multi-layer network with 4 layers, and this bound, these colors, each of them, they show the average norm of the gradients on each layer. So in the first layer, Wait, something is weird here. Oh, this is the speed of learning. Sorry. Yeah, this is not really normal of the gradient. Yeah, this speed of learning. Oh, never mind. Something is wrong about this. I have to figure out. But okay, but this was supposed to like inverse. So, but in practice, if you do this, if let's say you're gonna have a homework in order to derive the back propagation. If you can in fact do this experiment yourself. If you have a network with multiple layers, you can visualize the norm of the gradients in your network. In the earlier stages, the gradient is going to be big. As you are going back and back, in the earlier stages, the norm is going to be very, very small. Right? So this is called vanishing gradients. And there is this dual problem for this. If your gradients are bigger than some certain values, multiplying them together is going to make them super huge. It's called exploding gradients, obviously. So like gradients can be huge. Again, it's a question how to handle those gradients. What do they even mean? Right? Yeah, so in practice, people do a lot of, come up with different tricks for solving these issues. For example, one trick can be creating direct connections between earlier stages and final stages, like only for your training time for a few steps, if you face those kind of issues. Or another idea is there's another very popular family of neural networks. They're called LSTMs, or long short-term memory networks, or something like that. And they introduce extra hidden states with other meaningful connections between them, and they try to handle this issue of vanishing and exploding gradients in different approach. Again, we don't have much understanding of why they happen. They're designed only based on intuition, and the way they work, it's very intuitive. But we don't have like theoretical guarantees on proof for them when they work and when they don't work. So with this, we are almost done. If you have any questions, ask now, or if you're shy, you can come here after class.
So the vanishing gradient problem, does it also depend on the activation function you use?
It does. Yeah, it depends on that too. On the norm of that.
Yeah, because of the sigmoid, it's like it gets saturated and it becomes flat.
Yes, yeah.
How did you design those neural net architectures?
How
like did people design neural?
Oh, it was okay. So the whole story is that it was completely inspired by nature, by our brain structure. But then people like started like different neuroscientists also like have different observations about how brain works, which led into like different architectures of neural. Okay, so we are officially done. You can go. But if you have questions, come here.
So is there possible